Right, in this video we're going to talk about the column space and the row space of a matrix. So this is a continuation of the previous video where we talked about how whenever you have a matrix there are subspaces associated with it. One of them is the null space. The null space is the set of all vectors that get mapped to the zero vector by the matrix. And we have two more subspaces. So one of them is the column space of a matrix. So let's say, okay, so the column space and the row space. This is going to be a short video. This is just introducing what they are. So let's say that you have a matrix A. The column space of A, sometimes it's written like call A, there's no standard notation for the column space, is the span of the columns of A. And let's just practice using the definition. So how will we describe the column space without using the word span? It's the set of all linear combinations, right? That's what the word span means. It's the set of all linear combinations of the column vectors of A. And I'm using column and column vector as synonyms. Okay. And similarly, so this is a definition. So this is the first definition, and then the second definition is the row space of A, sometimes written row of A, is the span of the row vectors of A. Okay. Now how do we know that the column space and the row space are subspaces? Well, the column space and row space are spans of vectors, right? They're spans of a collection of vectors. And the span of any set of vectors is a subspace. So that explains why these are subspaces. So since the column space and the row space are spans of sets of vectors, they are subspaces. Now what space are these subspaces a subspace of? Well, if A is an m by n matrix, okay, let's just do an example. So let's say that A is, this 3 by 2 matrix, right? Well, we see that the column space, the columns have how many components? 3, right? This is a 3 by 2 matrix. The column space is a subspace of R3, and the row space is a subspace of R2, because the rows have 2 components. Let's draw a picture of the column space and the row space. So here's, now notice that A is a 3 by 2 matrix. When you multiply A by a vector, the input vectors have 2 components. So we have R2, we should put R2 here, and then R3, over here. And A will take vectors in R2 to R3. So let's look at the column space. It's 1, 2, 3. Okay, so maybe that's 1, 2, 3. And 4, 5, 6, I don't know, maybe it's that. Right? And so the column space is the span of these two. vectors, so you get this plane in R3. So this span, okay, right? That's the column space of A. It's all vectors of the form like C1 1 2 3 plus C2 4 5 6. Right? So that's the column space. It's a plane. What about the row space? Well, the row space, I have these two. So the row space of A, it's all vectors that have the form C1. Okay, so the first row is 1 4, and then the second row is 2 5, and then the third row is 3 6. So, okay, here's 1 4 maybe, and here's 2 5, and 3 6. And what's the span? The span is all of R2. The span is all of R2. So that's the row space of A. The row space of A is just R2. The column space is a plane. It's the span of 1 2 3 and 4 5 6. Now notice that the row space and the column space are completely different spaces, right? I mean, first of all, the row space is in R2 and the column space is in R3. I mean, that's the most obvious difference. And yeah, I mean, you just look at the picture. I mean, they're just completely different vectors, right? The column space, 1 2 3 is in the column space of A, but 1 2 3 is not in the row space of A. But one thing that they do have in common, so in general, the row space of A is most definitely not equal to the column space of A. These are completely different things. I mean, in general, the row space, if you have an n by n matrix, then the column space is a subspace of Rm, and the row space is a subspace of Rn. So they live in completely different spaces. However, notice that in this example they're both planes, right? The column space of A is this plane, and the row space of A is R2. We think of that as a plane. So, and planes are two-dimensional. So in general, the row space of A is not equal to the column space of A, but, okay, it's a theorem that the dimension of the row space of A is equal to the dimension of the column space of A. This is something called the rank theorem. Sometimes the dimension of the row space is called the it's the row rank of A. And sometimes the dimension of the column space is called the column rank of A. But now the theorem says that they're the same, and so this common number is called, so here's the definition, the rank of A. Okay. So every matrix has a rank. And in this example, okay, for this A, that A, the rank is 2, because the dimension of the row space is 2. Or you can say, if you want to look at the columns, the dimension of the column space is 2. So this is a rank 2 matrix. So the example above, A has rank 2. Okay, that's kind of the big fact about the row space and the column space. before maybe saying more, I want to emphasize the proper use of the terminology. Okay, so the row space and the column space, those are subspaces. And being a subspace, it has a dimension, right? So we refer to the dimension of a subspace, not the dimension of a matrix. We don't say that, the dimension of A is 2, okay? The dimension of what space? The dimension of the row space is 2. The dimension of the column space is 2, right? When it comes to rank, okay, that is a number, and it's the dimension of the row space, or the dimension of the column space, they're the same thing, and it's the rank of A. So we refer to the rank of a matrix. We don't say the rank of the row space or anything like that, or the rank of the column space. It's the rank of the matrix. So every matrix has a rank, right? Because every matrix has rows and columns. So it has a row space, has a column space. Those spaces have dimensions, and since they're equal, that common number is the rank. Now it turns out, and this is part of the proof of this theorem, that the row rank equals the column rank, is that the rank is also equal to the number of pivots of the reduced row echelon form of A. Let's just check in the case of the example that we did. We'll check this for A above. If you have this matrix, what was it? 1, 2, 3, okay. 1, 2, 3, 4, 5, 6. Those are the columns. What do you get when you row reduce? Well, you get 1, 4 here, and then you do row 2 minus 2 row 1, so you get 0 and -3, right? And then you do row 3 minus 3 row 1, so it's 0 and then -6. And then, so yeah, so you have two pivots. You have a pivot here and a pivot here. But, let's just look at the reduced row echelon form, because that's, there's only one reduced row echelon form, and that's going to be, okay, what do we do? We take the pivots and turn them to 1. So we scale, oh, sorry, this is not in echelon form. Oh dear. We have to also do row 3 minus 2 row 2, right? And that'll give you this. Okay. So we have two pivots here. I mean, I could already see that there's going to be two pivots from the second matrix, but technically that's not in echelon form. So this is an echelon form, right? But let's finish it in reduced row echelon form. So it's the -3. Okay, so you divide row 2 by -3, so you get a 1 here, and then you just make everything above at 0. So that's the reduced row echelon form of A, right? And we see two pivots, which matches what the theorem tells us. Okay, and maybe one more thing about the column space. So if you have a matrix A, okay, and you multiply by x, remember you are taking linear combinations of the columns of A to get the output AX. So we can look back at solving AX equals B. This has a solution. Right? This system is consistent if and only if B is a linear combination of the columns of A. That's an important fact that we talked about linear combinations. Now how do we incorporate the column space into this? So just, I don't know, just like an aside. This is an important remark, though. It's an important thing to note. Linear combinations of the columns of A, what's that? The set of all linear combinations of the columns of A is the column space of A. That's the word for it. So this is the same as saying that B is an element of the column space of A. So the column space of A is all the vectors B for which AX equals B has a solution. Right? So going back to this matrix, A, okay, if you have a vector like this, if B is on this plane, right, then AX equals B has a solution. If B is not on this plane, if B is like out here, then AX equals B does not have a solution. Okay, so that's an important thing about the column space. That's something that doesn't really apply to the row space, because when you're multiplying a matrix by a vector, you're taking combinations of the columns, not the rows. So somehow, in the theory, the column space, even though the definitions are symmetrical, the only difference is columns versus rows, somehow the column space is more important than the row space. Okay, that's it for this video. Thanks.